Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. I am Asra bin Samarazi. So today I would like to explain about assignment 2 for question 1A and 1B from A to E. Okay, first, read about the spring mass system and their motion as the following. As what I've been read, here I summarized what I'll be read. So, note that the position x is positive when the spring is below the equilibrium position. This means that velocity is positive when the mass is moving downward, falling in the direction of gravity. In the first picture, nothing is happening. In the second picture, the mass hangs still and unmoving. In the third picture, here is the picture. I'm sorry. Here is the picture. The first picture, second, and the third picture. Okay. Alright. So in the third picture, the mass is stretched and is currently moving or about to be released and begin its motion. The equation of motion comes from Newton's second law. Mass times acceleration is equal to the sum of the forces. Then the restoration force comes from Hooke's law. That is the distance the mass hangs from the natural length of the spring. This is called the equilibrium position for the middle picture. And x is the distance of the mass from equilibrium. We can say that x is equal to 0 at equilibrium. With only these two forces acting on the mass, we can write the differential equation, which is this one, where mg minus ki is equal to 0. Why mg minus ki is equal to 0? This is because the mass is 0, whereas the force of gravity mg equals to the force of the spring. Okay, for the question 1BA, the question is a mass weighing 64 pounds stretches a spring 0.32 feet. The mass is initially released from a point 8 inches above the equilibrium position with a downward velocity of 5 feet per second. So here is the calculation. Based on the explanation in A, we can know that this equation is equal to 0, or this equation and this equation is equal to 0. Given that we have been given the weight is 64 pounds as equal to 0.3 feet, distance is 8 inches, and time at 0 is equal to 5 feet per second. Based on the Newton's second law, I'm sorry, it's too big, so I'm going to make it smaller. Oh. Based on Newton's second law, W is equal to F restoring force, W is equal to Kf. K is the spring system. We substitute the information in the formula. So we got the K, which is spring system, is equal to 200. We also define as W is equal to mg, right? Then we know that m is equal to W over g. Then we substitute, we got 2 to that. Then we substitute the given information in the equation, where the equation is equal to 0. So we substitute the spring system that we got is 200, and we know the equation is homogeneous because it's equal to 0. So we can use second order differential equation, which is this one. Oh, what is that? Okay, and then after we got this equation, we use y, right? This equation is to find C1 and C2. C1 and C2. Now we convert to x. So at 0 is equal to minus 2 over 3. At 0 is equal to this one. So we got C1 is equal to minus 2 over 3. We have been given x upper from 0 is equal to 5. So we substitute in the equation above to find the C2, where we got half, 1 over 2. So we can write the order or the differential equation where x is equal to minus 2 over 3 cos tan t plus 1 over 2 sin tan t. So the next question is, what are the amplitude and the period of motion? Given the no coefficient, we can stop the amplitude of motion. So here is the formula for amplitude. We substitute the C1 and C2 we get in the previous question. So we got A is equal to 5 over 6. The period of motion is described by T equal to 2 pi over omega, where omega is equal to square root of K over 5 over M. So omega is equal to 10 and period is equal to pi over 5 seconds. The next question is, how many complete cycles will the mass have completed at the end of 3 pi seconds? From the equation, we know that t is equal to 3 pi seconds. T is equal to pi over 5 seconds for one complete cycle. So C is equal to T over period is equal to this one. So the final answer is 15 complete cycles. Next, at what time does the mass pass through the equilibrium position heading downward for the second time? Firstly, we need to solve it with theta first. Theta is equal to time shift tangent C1 over C2. Then we substitute the C1 and C2 in the formula. Then we substitute in the equation of motion where xt is equal to amplitude times in bracket omega times c plus theta. So after we substitute in the formula, we get that t time is equal to pi over 5 plus 0.0927, which is give us 0.7210 seconds. So that is the final answer. And the last question is, at what time does the mass attain its extreme displacement on either side of the equilibrium position? From previous question, we get this equation of motion. Xt is equal to 5 over 6 times in bracket 10 t minus 0.927. For extreme displacement, sign is given plus minus 1, where theta is pi over 2, 3 pi over 2, and etc. Thus, theta is pi over 2 plus n pi for all n is equal to 0, 1, 2, 3, and so on. So we substitute in the formula, then we get c is equal to pi over 10 in bracket 1 over 2 plus n plus 0.0927. So I think that's all from me. Thank you for watching.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nafisa Balkis binti Ahmad Amti, and I'm going to proceed with another question. Paper F. What is the position of the mass at t equals 3 seconds? So we have x equal to 5 over 6, 5 over 6 times upper bracket 10 upper bracket 3 and close bracket minus 0.927 in close bracket, and the answer is negative 0.5978. For G, what is the instantaneous velocity at t equal to 3 seconds? So we have the formula velocity here, and then we put in all the information given to this equation, then we get the answer negative 5.814 feet per second. And for h, what is the acceleration at t when it is equal to 3 seconds? We also have acceleration formula here. When we put all the information together, then the answer is 59.702 feet per second squared. To move to another question, which is what is the instantaneous velocity at the times when the mass passes through the equilibrium position. Okay, if x equal to 0, then you can see that t is equal to 1 over 10 bracket 0.927 plus n pi in the close bracket for n equal to 0.12, which is, we put it in the formula and then we can get the answer plus minus 25 over 3 feet per second. For j, at what times is the mass 5 inches below the equilibrium position? If x equal to 5 over 12, then we can see here 5 over 12 equal to 5 over 6 sine over bracket 10t minus 0.927 and close bracket, it is sine over bracket 10t minus 0.927 and then close bracket and equal to 1 over 2. We can conclude that either we can choose for formula 1 or formula 2, which the differences is there has 5 pi on the second equation and they have no pi on the first equation. So for the fourth case, at what times is the mass 5 inches below the equilibrium position heading in the upward direction? If x equal to 5 over 12 and b equal to x prime is below than 0, less than 0, then b is equal to 1 over 10 over bracket 5 pi over 6, then plus 0.927 plus 2 and 5 in the close bracket for n equal to 0.12.
Hi, Assalamualaikum. I'm Nur Shakila bint Amarizi, and I'm going to proceed for question 2, which is series circuit analog. So, I'm going to answer question 2b part 1, which is the question given is find the charge on the capacitor in an LRC series circuit at t equals to 0.01 second when L equals to 0.05 H, R equals to 2 ohm, C 0.01 F, and ET, which is ET is a voltage impressed 0 volt, given that Q0 equals to 5C and I0 5 coulomb, and for the current given is 0 ampere. So actually this Q0 is the charge for the capacitor. Determine the first time at which the charge on the capacitor is equal to 0. So we have to determine the first time at which the charge on the capacitor is equal to 0. So the Q is equal to 0. So as we recall the Kirchhoff's second law, impressed voltage ET on a closed loop is equal to the sum of voltage drop in the loop. So we have the equation here, which is the linear second order differential equation, which is L d squared Q over dt squared plus R dq over dt plus 1 over CQ equals to ET, which is ET is the voltage impressed. So we have all the information here and we substitute into the equation and it becomes like this. So to make it easy, we want to make it like this equation here, this quadratic equation here, in this form, which is the highest power is squared and the coefficient is 1. So we divided everything with 0.05 and we get this equation: d squared q over dt squared plus 40 dq over dt plus 2000 q equals to 0. So it is exactly like this form, which is m squared plus 40m plus 2000 equals to 0. So what we have here is using the formula to find the amount or the value of m. So what we have here is m equals to negative 20 plus minus 40i. I is the current. So we have here qt, which is the charge of the capacitor. So this is the equation for the charge of the capacitor, which is e exponent to the power of negative 20t. This is the factor. Okay, times c1 cosine 40t plus c2 sine 40t. Okay, we recall here from the notes given, we have q prime t equals to it. So the derivative of qt equals to it. So it, to get it, we can derive the qt equation. So we have here negative 20 exponent to the power of negative 20t times c1 cosine 40t plus c2 sine 40t plus exponent to the power of negative 20t times negative 40 c1 sine 40t plus 40 c2 cosine 40t. As we have from the question given, which is when q0 equals to 5 and I0 equals to 0, so we substitute into the equation and we can get the value of C1 here. C1 equals to 5 and C2 equals to 5 over 2. So we can substitute back into the equation of QT to have a complete equation here. So when T is 0.01, so we have here the value of Q is 4.568 coulomb. Okay, the first time the charge is 0. So we take the equation of the QT and equals to 0 because the first time the charge is 0. But the factor exponent to the power of negative 20t will never be 0. So, so we have this here. This is what's left. 5 cosine 40t plus 5 over 2 sine 40t equals to 0. So we divide by cosine 40t, and to make it simple, we have 5 plus 5 over 2 tangent 40t equals to 0. And tangent 40t equals to negative 2, which is tangent is negative in the second quadrant and fourth quadrant, but we take the first, second quadrant. So 40t equals to 2.03444, and we have t here equals to 0.0509 second. Okay, the next question is find the steady state charge and the steady state current in an LRC series circuit when L equal to 1 H, R equal to 2 ohms, C equals to 0.25 F, and the voltage impressed equal to 50 cosine T V. So, like the previous question, so we have this equation, which is the linear second order differential equation. So we have the information given and we substitute into the equation, and we get d squared q over dt squared plus 2 dq over dt plus 4q equals to 50 cosine TV. This is congruent to this quadratic equation here, which is m squared plus 2m plus 4 equal to 0. So the value of m is -1 plus minus Z3i. So the equation for QC is like this. Okay, you have exponent here, the factor, and the cosine part and the sine part. So we have to find the particular solution using the method of undetermined coefficient. So we have the impressed voltage here, ET equals to 50 cosine TV. And we have QP here, A cosine T plus B sine T. So for derivative of QP, we have -A sine T plus B cosine T. And for the second derivative of QP is -A cosine T minus B sine T. So we just substitute all the informations here into the original equation. And we have something like this. This is the simple part of the equation. So by comparison, we get 3a plus 2b equals to 50 and 3b minus 2a equals to 0. Okay, where do we get this 3a plus 2b and 3b minus 2a? So this is from the properties of trigonometry. So solving the equation simultaneously, we have a equals to 150 over 13 and b equals to 100 over 13. So we substitute into the equation of QP and we have something like this, which is 150 over 13 cosine t plus 100 over 13 sine t. The particular solution for Q is the steady state charge. To find the steady state current, so we have to derive the QP because this QP is for steady state charge, and to find the steady state current, as I mentioned earlier, is to derive the QP, derive the charge equation. So we have something like this. And so these are the answers for steady state charge and steady state current. So thank you.
3. Find the steady state charge and the steady state current in a LRC. In a LRC series circuit, when the impressed voltage is ET equal to E naught sine gamma t. We can see here the steady state charge is a particular solution of the differential equation. As you can see, there is the formula. Using the method of undetermined coefficients, we assume that it is particular solution of the form QPT equal to A sine gamma t plus B cos gamma t. And then we substituting this expression into the differential equation and simplifying and equating coefficient given. You can see here there are A and B for the expression in the differential equation. It is convenient to express A and B in terms of some new symbols. Okay, if x equal to L gamma minus 1 over C gamma, then x squared equal to L squared gamma square minus 2L over C plus 1 over C square, and then gamma 2. Then we can see here, therefore A equal to E naught x over minus gamma z square in close bracket, and for B we can get E naught R over minus mod z square in close bracket. So the steady state charge is QPT equal to negative E x over gamma z square sine gamma t minus E naught R over gamma z square cos gamma t. Now we can see that the steady state current is given by IPT equal to Q prime PT, which is the equation below. and then the quantity x equal to L gamma minus 1 over C gamma, and then Z equal to square root x squared plus R squared are called the reactance and impedance respectively of the circuit. Both the reactance and the impedance are measured in ohms. Thank you.